Hello, welcome to Math Matters. Got a little something for everybody today, so why don't we just get right after it. I want to start today by talking about graphical data representations. You're taking data and you're putting in some kind of picture. We see this a lot in newspapers when a survey has been taken or some information has been gathered. They'll put this in the newspaper in some kind of nice graph. And you have to be careful about this because they can mislead you by the way they present the data. So I want to look at some examples today of misleading data. There's actually a lot of ways to lie using statistics. There's at least one book that I know of devoted to it, How to Lie with Statistics by Darrell Huff. It was required reading back when I took statistics. And it has a lot of things mentioned in there. And some of them are computational. Some of them are ways to manipulate the data in such a way that it misleads. But the ones I want to focus on today are simply the graphical kind of things that you can do, trying to tricking your eye into tricking your brain, I guess is the idea. So let's look at an example. One trick that people can use or folks can use to mislead you is they can use a narrow range in graphs. Now, suppose you have a data set where the change over a period of time is very small, and I'll just flash up some data where that's basically flat. You know, from 2002 to 2006, there's not much change there. Well, watch what happens if I change, and I'm going from 0 to 10 along the y-axis here. Watch what happens when I change the range on that axis. Yeah, if I change it from 9.8 to 10.3, then all of a sudden it looks like it's increasing dramatically. You know, there's something bad is happening, or something good is happening. We have to convince the public about this. It's the same data. The only thing that has changed is the way we position things along this y-axis. So you've got to be careful about this. You've got to keep your eyes open to problems like this where they kind of go through and they're not. One tip-off is most of these things should start at 0 down here at the bottom. If they don't, there's a good chance that you're being manipulated on that. That's one of the oldest tricks in the book. I can take it one step farther and just completely remove marks from the graph whatsoever. Have you ever seen an ad something like this? This is my dramatic TV ad. Our customer satisfaction ratings are going through the roof. And I like this little part, they even put a little arrow here to say, yeah, it even went higher, but we got tired of drawing it, you know, this kind of thing. So, but if you'll notice, there's no markings on this graph whatsoever. So what is this telling you? What is it telling you? What are we measuring through here? Time? I don't know. Cars sold? I don't know. And then on the other axis, there's no markings. Satisfaction? How do you measure satisfaction? Do they give a survey? Are they counting the number of people who didn't report them to the Better Business Bureau? And what's the scale? Did they start at 0? I don't know. See, there's really no way to gauge what's going on in this graph whatsoever. And that is something to kind of watch for. That's a tip-off right there. If there's no markings, then the graph is meaningless. And I even went one step farther and made the graph narrow so that it even looks like it's even steeper. You know, the increase is even steeper. Just a couple things to watch for. Another little trick that they can use or folks can use to mislead you is the idea of showing linear change, but showing it with volume. And I notice things like USA Today, they're very creative with their graphs. They do a lot of these kind of things. And it's okay as long as you just change one dimension. Let me give you an example. I don't know exactly what I'm measuring here, but in 2005 there was one of these things. And so I'm using a three-dimensional bar to indicate that. Now in 2006 it doubles. Let's say that it doubles. So it'll go up to 2. Now if you'll notice, I kept the dimensions of the base the same. The only dimension I changed was the z dimension, the up and down dimension. And when I doubled that, it actually doubles the volume. And that's a true representation of the doubling of the data. Okay? Now here's the way I could mislead you on this. I could double every dimension. Okay, not just the up and down dimension, but the left and right and the back and forth dimension. That would look like this. What happens here, yes, the amount has doubled, but if you look at the volume of this, what your eye perceives is the volume of these objects. And what has happened when you double each of these dimensions, you've got doubled it here, you doubled it there, you doubled it there. 2 times 2 times 2 is 8. So the volume of the shape shown, the solid shown, is actually 8 times the volume of the original shape. And so, yes, it's 2 times higher. But what your brain picks up is, wow, that's a big change. That's a factor of 8 change, when really that's a misleading part of the data. I've got one more to show you. This one's a little more computational. Odd-shaped pie graphs. And again, USA Today is great about doing this. A circle graph or a pie graph or a pie chart, people use different terminology for this. But you can get the area of the entire thing simply by taking percents of 360 degrees. So this 20% represents 20% of the entire area. And to get that out of the circle, I took 20% of 360 degrees and got 72 degrees. I'm getting my angle measures here. And again, with 25%, it's easy to calculate these things, and it's a true representation of what percent of the data is going into each category. A pie graph is a good picture to use when you're breaking data down into categories. But now what USA Today and some newspapers will do is they'll say, a circle is so plain. Let's do something creative. We're talking about the US dollar, so let's do a dollar graph. Or if it's chicken sold at KFC, chicken graph or whatever it is. Now, if you'll notice, I didn't change any of the angles. Okay? But because this boundary is no longer equidistant from the center, I have changed the percentages that go in each category. Even though I still have it marked at 20, it's not 20%. I actually had to use a little calculus to calculate this percentage. It's more like 17%. And that's because it gets out to the boundary a little quicker than some of these others do. Instead of 25%, that's more like 31%. Instead of 40%, this is more like 43% of the entire area. And the last one, that's more like 9%. That's the kind of mistake that could be made inadvertently by a journalist or a graphic designer that didn't pay enough attention in their math classes, didn't learn these little tricks. But it could also be used to mislead you. Those two categories where the actual percentages are less, you could come back and say, hey, I told you it was 20%, but what you told my eyeball was that it was less than that. Okay? So it can be used to mislead, and that's the thing I'm kind of watching for. I'm going to flash up some summary slides that kind of talk about these things, and then we'll move on to the next topic.